A few months ago, I noticed something strange sitting on top of a wood stove. It looked like a small ceramic tile, two wires coming out of it, and a USB cable plugged into the other end. The phone connected to that cable was charging. There was no battery pack, no solar panel, no generator running outside, just a tiny device sitting on hot metal. At first, I assumed there had to be some kind of hidden battery somewhere in the system, but there wasn't. The device itself was generating electricity from heat. And the strange part is that the heat wasn't coming from anything new. The stove was already burning. The firewood was already producing heat the entire time. For years, that energy had simply been escaping into the air. Now it was charging a phone. The entire setup cost about $15 to build. And once you understand how it works, you start noticing places where the same trick could work almost everywhere. Wood stoves, campfires, vehicle engines. But the really surprising part is this. The same principle behind that tiny device is currently powering spacecraft billions of miles away from Earth. And that's where this story actually begins. In 1977, NASA launched two spacecraft that were never expected to still be operating today. Voyager 1 and Voyager 2 were sent toward the outer edges of the solar system, far beyond where sunlight is strong enough to power solar panels. That created a serious problem. How do you generate electricity when the sun becomes too weak to use? Solar panels wouldn't work. Batteries eventually die. Fuel-based generators require moving parts and maintenance. NASA solved the problem with something far simpler. They used thermoelectric generators, devices that produce electricity from a temperature difference. Inside each Voyager probe were systems with no moving parts at all. One side of the generator stayed hot. The other side stayed cold. That difference in temperature created electricity continuously. When Voyager launched, the system produced about 470 watts of power. Nearly 50 years later, those spacecraft are still transmitting signals back to Earth, powered by the same simple principle that a small $15 device on a wood stove can use right now. The physics behind this device is actually very old. In 1821, a German physicist named Thomas Seebeck discovered something unusual while experimenting with different metals. He found that when two conductive materials were connected together and one side became hotter than the other, a small electrical voltage appeared between them. No fuel, no motion, just heat moving from one side to the other. This became known as the Cbeck Effect. Scientists understood the discovery almost immediately. Engineers experimented with early thermoelectric generators throughout the 1800s, but the technology never became widespread. The reason was simple. As electrical grids expanded during the 20th century, power plants began producing electricity at enormous scale. Homes and businesses could suddenly access cheap energy simply by plugging into the grid. Generating small amounts of electricity locally stopped feeling necessary. So thermoelectric systems quietly remained in specialized fields like space exploration, military equipment, and remote scientific instruments. And for most people, the idea was almost completely forgotten. The device that makes this possible is called a thermoelectric generator, or simply a TEG module. At first glance, it doesn't look like much. It's a small ceramic tile, about the size of a large postage stamp, with two wires coming out of it. Inside that tile are dozens of tiny semiconductor junctions designed to react to temperature differences. The concept is extremely simple. One side of the module gets hot, the other side stays cool. When heat begins flowing from the hot side to the cold side, electrons inside the material start moving. That movement creates a small electrical voltage across the wires. No turbines, no magnet spinning, no mechanical motion, just heat moving from one place to another. The larger the temperature difference between the two sides, the more electricity the module produces. That's why something like a wood stove works so well. The surface of the stove is hot, while the surrounding air stays much cooler. That temperature gap is exactly what the module needs to start generating power. The module most commonly used for small DIY builds is called the Tech 12706. You can find it on Amazon or AliExpress for around $8. It's a small ceramic tile containing 127 thermoelectric junctions sealed inside. When one side becomes hotter than the other, those junctions begin producing a small electrical voltage. With a temperature difference of about 60 degrees Celsius, the module usually generates somewhere between 2 and 3 volts. That's useful, but not quite enough to power most devices directly. So the second component in the system is a small DC to DC voltage booster. These cost about $5, and their job is simple. They take the low voltage from the module and step it up to a stable 5-volt USB output. Once that booster is connected, you can plug in a USB cable and charge things like phones, battery banks, or small LED lights. Total cost for the entire setup? About $15. Putting the system together is surprisingly simple. Start by placing the thermoelectric module directly on the hot surface you want to harvest energy from. A wood stove works perfectly, but any stable heat source can work. Before placing it down, add a thin layer of thermal paste to the bottom of the module. This improves heat transfer by filling tiny air gaps between the module and the metal surface. Better heat transfer means a stronger temperature difference, which means more electricity. Next, attach a small aluminum heatsink to the top of the module. The heatsink helps keep the top side cooler by releasing heat into the surrounding air. Now connect the two wires from the module to the input terminals of the voltage booster. Finally, plug your USB cable into the booster. When the stove heats up, the bottom of the module becomes hot while the heatsink stays cooler. The temperature difference generates electricity, and the booster converts it into a usable USB power output. The small $15 setup is a great way to understand the principle, but once people see it working, they often start thinking about how far the idea can go. A friend of mine did exactly that. After we built the first module together, he decided to expand the system at his off-grid cabin. Instead of using a single thermoelectric tile, he installed 8 modules around the metal flue pipe of his wood stove. Each module fed electricity into a small voltage regulator connected to a compact battery bank. Whenever the stove was burning, the system quietly generated power, not huge amounts, but enough to be genuinely useful. It runs the LED lighting inside the cabin, keeps his phone and radio charged, and slowly tops up the battery bank he uses for a small water pump. The stove was already producing heat every night during winter. The only difference now is that a small part of that heat is no longer wasted. The wood stove example is probably the most obvious place to use a thermoelectric generator. But once you understand the idea, you start seeing opportunities almost everywhere. Take camping, for example. If you're cooking over a small camp stove or sitting around a fire, there's a constant temperature difference between the hot metal surface and the surrounding air. A single module placed near that heat source can generate enough power to charge a phone or run a small LED light. Another interesting use is vehicle engines. Engines produce large amounts of heat that usually leave through the exhaust system. Mounting thermoelectric modules near those hot metal surfaces allows them to generate electricity whenever the engine is running. And then there's a surprisingly unusual example: compost piles. During decomposition, active compost can reach temperatures of 55 to 70 degrees Celsius inside, while the outside remains much cooler. That temperature difference is enough to generate small amounts of electricity for garden sensors, timers, or small lights. Now it's important to be realistic about what this technology can actually do. A single thermoelectric module is not going to power your entire house. It won't run a refrigerator, an air conditioner, or replace the electrical grid. The amount of electricity produced by a small module is relatively modest, but that doesn't mean it isn't useful. What these devices do extremely well is capture small amounts of energy that would otherwise be wasted. If you're already burning wood for heat, running an engine, or cooking over a stove, that heat is being produced anyway. Most of the time, it simply escapes into the air. A thermoelectric generator just sits quietly in the middle of that heat flow and converts a tiny portion of it into electricity. That electricity might power LED lights, charge a phone, run sensors, or slowly charge a battery bank. It's not about replacing big power systems. It's about recovering energy that was already there. What makes this technology interesting isn't just the small amount of electricity it produces, it's the way it changes how you start looking at energy. Most of the time we think of heat as something that simply disappears. A stove warms a room, an engine runs, a fire burns, and the extra heat fades into the air. But heat is actually energy in motion. It's energy moving from a hotter place to a colder one. And whenever that movement exists, there's an opportunity to capture a small part of it. That's exactly what NASA did with the Voyager spacecraft. More than 15 billion miles from Earth, those probes are still transmitting data using electricity generated from a temperature difference. The tiny device on a wood stove obviously isn't sending signals across the solar system, but it works on the exact same physics. And once you understand that principle, you begin to notice heat sources everywhere and realize that some of that energy doesn't have to go to waste anymore.